drift stars.
Yeah.
We're So hi everyone, let's get started. Welcome to our very last HotSci of the summer. So I'm Ivana, and we also have our two other HotSci organizers, Ryan and Barman here, for our last installment. So today we'll be focusing on ISM feedback, both in the context of galaxy evolution in terms of the mass-Metallicity relation and also massive star formation. So our first speaker is Kalina, and our second speaker will be Calum, Hawcroft, both of whom are postdocs here at Space Telescope. So you can take it away.
Yeah, thanks so much. All right, well, hi everyone. Thanks so much for being here. Can you all hear me okay? Yes, great, thanks. Yeah, so thanks for that introduction. As Ivana said, my name is Kalina Nedkova. I'm actually a postdoc at JHU across the street. It's okay. But I work with Mark Rafalski here at Space Telescope, so I totally get the confusion. And I also want to highlight significant contributions from several other people that have made this work possible, including Mitchell Rafalski, Farhan Hassan, Elena Henry, Greco Oyorzun, Ilyas Guverts, Alex Beckett, and the larger PASSAGE collaboration. And I will be telling you about all of the science that the PASSAGE data is enabling today. So you might have heard me give talks here before on UV candles, on understanding the effects of dust on galaxy sizes at different wavelengths. But today I'm going to be talking about something different. And this is my second project that I've been focusing on here during my postdoc. And it's on the mass-metallicity relation of low mass galaxies at redshifts less than 3.4. And so I wanted to start today by showing you some of our PASSAGE data. So here I'm showing you, we have fantastic direct imaging. You can see that we have these beautiful galaxies. And we also have GRISM spectroscopy. And so you can see in the dispersed image that the light from every single object in our field of view gets dispersed along a particular direction. And these data have really been a treat to work with because they are just so rich. And so just by looking at this, you can already see a few emission lines here. I understand maybe you haven't looked at these as much as I have, but I'm just going to point out a few. You can see, for example, there's some emission features there. There's, probably something here. So without even doing some kind of analysis, we can already see these beautiful emission lines in these data. And so let me tell you a little bit more about the PASSAGE survey. So PASSAGE is a pure parallel survey, which means that we obtained our observations at the same time as other programs, which really helps maximize the scientific return of the telescope. In total, we obtained 63 independent fields. I'm showing you the locations of those fields here. And we have 3 GRISM, 2 GRISM, and 1 GRISM coverage. And those are indicated by the color coding. But if you count up all of these boxes here, you will not count 63. And that's because a lot of our fields are close to each other. And so in this plot, they overlap. It turns out that astronomers are really interested in areas like cosmos. And so if we zoom in on the cosmos field here, you can see that we have about 10 fields that overlap with the Cosmos Web footprint, and about 15 that overlap with the HST ACS footprint. And so these are fantastic because although we have very deep imaging as part of PASSAGE, it is at most 3 filters. And so having this ancillary data where we can take advantage of imaging at different wavelengths really helps constrain our SEDs so that we can measure physical parameters like stellar masses. And so in total, we have 13 fields with 3 Grism filter coverage, 22 with 2 Grism filter coverage, and 28 with just 1. And that is because we were restricted to change filter setup only when the primary program was doing the same. But despite this, we are getting fantastic data, and we're also following up a lot of our PASSAGE fields with ground-based and space-based instruments, and so we will make use of a lot of these fields. One thing that's also really important is having multiple orientations. You can imagine if you have 2 objects that are side by side and you disperse the light in one direction, the spectra are going to be contaminated. But if you disperse also at a 90-degree angle, now you're going to be able to extract those spectra of the 2 objects cleanly. This also helps with things like spatially resolved maps of emission lines. And so these data are really fantastic. But one of the reasons why I'm really interested about PASSAGE is because you can think of it as a pathfinder for Roman. And so here I'm showing you our 3 Grism filter transmission curves. And here are Romans at 1 to 1.93 microns. You can see that they are very similar, especially at the blue end here. And so our data with PASSAGE are truly fantastic. Here I'm showing you, this is a spectrum of a galaxy. It is chosen to be pretty nice, but you know, we get these pretty regularly. We find these about 1 every 20 objects. We see a very nice spectrum like this. This galaxy happens to be about a redshift of 1.8. And what I'm showing you here is the observed wavelength on the x-axis, the flux on the y-axis. The black spectrum, the black histogram here shows you the spectrum of the galaxy. And we have a custom line fitting tool that was originally developed by Elena Henry that we have since updated to work with JWST Grism data. And the fit from that line fitting tool is shown here in red. And so you can see that we are nicely fitting our emission lines, and we're detecting a lot of them. One thing to note is that this nearest Grism data has about a resolution of about 150. With Roman, it'll be a little bit higher. This will be really nice for things like deblending the H beta and the O3 line. So you can see here that they overlap a little bit. At this improved resolution, we'll also be able to cleanly deblend the O3 doublet. So this will be very exciting. But while we wait for that, PASSAGE is still enabling a lot of really exciting science. One thing so these are 3 different science cases. There's more, but I'm just going to touch on these just to show you the breadth of the science that's being enabled. So we can study the chemical composition of galaxies to constrain the baryon cycle. I'm going to spend the rest of my talk on this, so I'm going to skip it for now. We are also detecting brown dwarfs. And so here I'm showing you in this histogram the number of brown dwarfs we expect to detect per pointing. So with 63, you can imagine that we're going to have a very healthy sample. And we're detecting these in different parts of the galaxy, of the Milky Way galaxy. So in the thin disk, the thick disk, and in the halo. And these brown dwarfs are really important because they retain the chemical composition with which they are born. And so they're fantastic for tracing the chemical enrichment history of the Milky Way. Now, PASSAGE is also really special because it has very deep Grism spectroscopy in 3 filters, up to 3 filters in multiple orientations. And so what this enables us to do is look for high redshift galaxies at the epoch of reionization. And so I'm highlighting here a recent paper that we just published as part of the Passage collaboration. And what you see here, so what we did was we did a blind search for Lyman alpha emitters. So we did not use the direct imaging at all, and we only searched for emission lines in the GRISM data. And so here you can see that this object was detected in the imaging. You can see it's pretty compact, but where we actually found it was in the GRISM. And so here I'm showing you one orientation in the F115 filter. You can see we have a nice emission feature. What makes this really convincing is that we also see it in the other orientation at the same wavelength. And then in the other two filters, we do not have any emission lines, which gives us more confidence that this is truly a Lyman alpha emitter at a redshift of about 1.7. And so Passage is really unique because it enables this kind of science. And there's currently very few programs that have the setup needed to do this kind of search. And so future pure parallel programs are needed to advance this science case by adopting a strategy of obtaining very deep GRISM spectroscopy in multiple filters in multiple orientations. And so really JWST is the only instrument that can do this, because with Roman we won't be able to go as deep. Okay, I'm now going to focus in on the chemical composition of galaxies to constrain the baryon cycle. Okay, so I'm sure all of you have seen this about 1 million times, but I'm just going to walk through it very briefly just to set the stage. So what we are seeing here is a galaxy here in the inner 30 kiloparsecs or so. And so what we have is we have filamentary accretion of metal poor gas from very far away from the galaxy onto the galaxy. This accretion of gas triggers star formation within the galaxy, which produces stars which themselves synthesize heavy elements and enrich the interstellar medium. And then outflows here expel the enriched gas away from the galaxy. However, this is really complex. You can see that some of this expelled gas actually gets recycled back onto the galaxy. And these processes don't necessarily happen sequentially. They can occur at the same time. And so this is really complex and hard to model well. In fact, we heard a talk earlier in this HotSci series about moving away from the simple cartoon onto more realistic simulations. But one thing that I think will be easy to get behind is that these processes depend on the mass of the galaxy. And so you can imagine if you have a very massive galaxy, it's going to have a very deep potential well. It's going to be very efficient at accreting this pristine gas compared to a lower mass galaxy that has a shallower potential well. Higher mass galaxies will also have less efficient outflows because they are more gravitationally bound. And so you might expect that there might be some kind of a connection between the metallicity of a galaxy and its stellar mass. And indeed, this is the mass-metallicity relation, or the MZR. What I'm showing you here is the stellar mass on the x-axis. We have gas phase metallicity on the y-axis. In general, low mass galaxies are also have less metallicity. On the other end, higher mass galaxies are more metal rich. And this is because, again, this is controlled by the baryon cycle, where the low mass galaxies, they are less efficient at accreting this pristine gas. They have, therefore, lower star formation rates, and their outflows are more efficient. And on the high mass end, we have more accretion of pristine gas, which leads to more star formation, more enrichment. And so this baryon cycle not only influences the MZR, but it also likely influences the morphology of galaxies, or the way that they appear. And so you can imagine if you have inflows of gas, they might create a star-forming clump within the galaxy. And so is there some kind of connection between clumpy structure and the NZR? So this is something that we're currently working on, and more results will follow shortly, but I just wanted to highlight that this is a very exciting thing to look into. And indeed, we're not the only ones thinking about this. There was a paper very recently on the metal pore star-forming clumps using, again, JWST nearest. And what they found was that the star-forming clumps, which you can kind of make out here, you can see that they have higher star formation rates, and they are also more metal pore than the rest of the galaxy. And so with PASSAGE, we will do this for larger samples. We are also able to do this at much higher redshifts than done here. And so this is work that Farhan will be leading as part of PASSAGE. And I myself am interested in the integrated properties of these galaxies. So do galaxies with clumps on an integrated scale, do they lie on a different part of the mass-metallicity relation than galaxies that don't have clumps? So PASSAGE will let us know. So far, I've been talking about metallicity, but I haven't actually told you what I mean when I say metallicity. So all I mean is the abundance of oxygen relative to hydrogen. And going forward, you'll see it written in this way, where higher values indicate more metal-rich systems. And the way that we measure this metallicity is, of course, from the spectra. And so we're using three key diagnostic emission lines, the O3, the H beta, and the O2. And these are the so-called strong emission lines because you can see that they're really quite powerful in the spectrum. And with PASSAGE, we are able to measure these three emission lines. Because of the way that the filters are, we can measure them in two different redshift ranges that are highlighted here in yellow. And these intermediate redshifts are really key because Mitchell-Rowalski recently led a paper using the MUSE Ultra Deep Field, which has some of the deepest HST GRISM spectroscopy, as well as about 140 hours of MUSE data. And what he showed was that the strong line calibrations are valid at these intermediate redshifts by comparing them with the direct metallicity method. Okay, so why is this important? So here I'm showing you just some recent results from various different works. What I want you to notice is that the black line and the pink line here are from JWST. All other works here are based on other data sets. And so one thing to notice is that the slopes of these two relations are slightly shallower than the ones that we have been obtaining previously. And these are also the ones that are probing the lowest mass ranges. And so this change in slope could either indicate that there is a change in the baryon cycle, or there is some kind of nuance in the calibrations that we're using. And so understanding which one is driving these differences in the slopes that we're seeing is still an open question. And so PASSAGE is fantastic for addressing this. And so here are our individual objects for one single PASSAGE field. I told you we have 63. Of those 63, I think about 40 are going to be spectacular, and they're going to have reliable stellar masses and reliable emission line measurements. And so from those, you can imagine that we're going to fill out this phase space very well. But one thing to note here is that there's a lot of scatter, right? And that's because all of these different galaxies have different star formation rates, and we are measuring different line ratios for these. And so one way to get a representative metallicity at a given mass is to stack these by stellar mass. And so that's what we've done. So here I'm showing you 4 different mass bins with the lowest mass bin here at the bottom and the highest mass bin here at the top. One thing that you can notice is that the O2 strength becomes stronger for the higher mass galaxies, and this is something that we expect. And so if we now plot the relation for these mass bins, here's where they lie. They line up extremely well with the Rafalski result from 2024. And although this is still preliminary and we are augmenting this sample, you can see that we see no evidence of a flattening in the slope of the mass-metallicity relation at low stellar masses. And soon we will have statistics from about 40 fields, so stay tuned. So one of the challenges and why I'm not showing you results from 40 fields is that obtaining stellar masses is quite challenging given our data set. And so we have been leading a lot of follow-up campaigns. So where available, we've been using archival data. I'm very happy to share that we also had a cycle 31, HST program that followed up 7 passage fields. And we've just been approved for a cycle 33 HST snapshot program where we're going to get F814W imaging of all passage. And out there is a cycle 2 program that's quite similar in setup. I'm also the PI of 2 NASA Keck proposals, which we obtained 3 semesters of time to follow up 12 fields, and we are also following up the southern fields with VLT. And so these fields are going to have a wealth of data, and we'll be able to really fill this in better. And this is really important because once we have the samples needed, we can then begin to study galaxies at a given mass as a function of morphology. Okay, so looking forward, I'm very excited to do this with Roman. One thing that I'm really excited about is this high latitude wide area survey that's going to cover 2,400 square degrees, and it will measure key emission lines. So these 3 key emission lines at redshifts 1.7 to 2.8. And then if we play a game where we take the stellar mass function times the detection rate that we expect from Roman, we can get the number of emission line galaxies that we expect to see. And so I'm going to look at O2 because this is one of the weakest lines for low mass galaxies. And if we do that, we get that Roman will detect about 500,000 galaxies with O2 emission lines. And so just to give you a sense of what this looks like, so here I'm showing you this mass distribution of these expected detections. For the ones shown here in purple, we will also be able to get morphological measurements because these will also have very deep imaging. And here's passage. So you can see the difference in scale between what Roman will get and what passage is giving us. But one thing that I really want to emphasize is that passage and JWST remain absolutely critical at the low mass end. Roman will not go as deep, and it will not be able to inform us about this low mass end of the mass-metallicity relation. So really, JWST is really fundamental for this. And so I just want to end by saying that passage is already revealing the details of the baryon cycle at low masses and low metallicity. Stay tuned for more. We have a lot of work ahead of us, but I think this is already showing some very exciting preliminary results. And I just want to emphasize that this low metallicity regime is of great interest and has recently been proposed as the topic for the 2026 Spring Symposium. So please be sure to vote, especially if you want to hear more about science like this. All right, thank you so much.
Okay, questions for Kalina?
Yes. Well, thank you so much for this presentation. It was wonderful. I really liked it.
Thanks.
One of the questions I had was when you were showing the scatter in the mass-metallicity relationship, and you managed to get rid of that scatter by stacking, which was great. One of the questions I had was, how did you calculate metallicity? And do you think that the scatter which we see here could be due to some uncertainties on the metallicities? Because I saw in the spectrum which you showed a couple of times where we did not have the oral 4363 line detected.
That's right.
It is blended with
Blended.
gamma. So you did not have the direct metal metallicity.
You're right. Yes. Thank you so much. That's an excellent question. Yes, you're right. I should have mentioned, so we are using a Bayesian method that was originally developed by Elena Henry that uses 3 strong line calibrations. It uses O3 over H beta, O2 over H beta, and then I think O3 over O2. I can double check for you. But so yes, and so this Bayesian approach gives us the most probabilistic metallicity. And so that's what I've been using to measure metallicity. And so that's why I've been focusing so much on these validity of the strong line calibrations at these redshifts. Yeah, that's a great question. Yeah, Dan.
Yeah, excellent talk, great work. So what about getting to even lower metallicities? You've got just the one field here, you'll be doing, 40 or 60 more.
Yeah.
And you also mentioned, I guess that the data could do it. You can see where you just have the Balmer lines and you don't see as much, oxygen or neon. And what about with Roman? I mean, you could go deeper. I mean, have you thought about, what it would take to, propose to go deeper and get down to these lower masses?
Yeah, that's also a fantastic question. So I've just been thinking about the High Latitude Wide Area Survey because it's one of the key surveys that Roman will do. I don't think I'm the person to ask about proposing for very deep Roman observations, but if that's something that you want to do, I would absolutely love for you to do that. That would be fantastic data, absolutely, yeah.
Yeah, great talk.
Yep.
I wanted to know if you can mention again how you explain the difference between the previous results that show a flattening of the region and your results that don't show this flattening.
Yeah.
Where the difference might be.
Yeah, thanks. Right, so one thing that I didn't touch on is that these also have different intercepts, right? So the intercepts can mostly be explained by differences in star formation rate and different redshifts. So if you ignore the differences in the intercept, you notice that if we look at, let's say, less than 10 to the 9, you notice that the HST results lie on slightly steeper relations than the more recent JWST results, which are a little flatter. And so what this tells us is that this could be due to differences in, for example, the way that outflows are expelling gas from galaxies. So is there some mass at which these mechanisms are different? And so what we find with passage is that at least down to about 7.5, we do not see a change in the slope. And so what this tells us is that from the high mass end to about 10 to the 7.5, we're not seeing a difference in the baryon physics that's happening. But I don't know, maybe as we add more data and as we complete our sample, maybe we will find something at even lower masses where we see a difference. So stay tuned.
Okay, last question from Chris.
Yes, quick one. Looking at the prism filter through bits,
yeah,
they're very like a factor of 2 or so by the looks of it. So Yeah, from like 0.25 to almost 0.5.
Yeah.
I guess that means your sensitivity therefore varies as a function of metallicity and of selection function.
Yeah.
Are there any kind of blind spots you have to worry about? Are there any populations which this makes you less sensitive to, or can you just or model through as you compare?
That's a really great question, and one that I haven't thought about. But no, well, I mean, yes, our throughput changes, but we still have high confidence in the emission lines that we're detecting. I haven't worried too much about the change in the throughput, but maybe that's something that we can chat about later if you have thoughts, or it's something. Yeah. Okay. Thank you.
All right. Let's thank Kalina again.
All right. Hi, everyone. Thanks for having me. Thanks for the introduction. I'm Calum. I'm a postdoc here, and I mostly actually these days work on population synthesis of massive stars, so trying to get predictions of properties of galaxies that are star forming and have these massive populations. But today, I want to talk to you a little bit about individual stars. So this is stuff that I kind of was working on before and also alongside this project. And a really, I think, super interesting problem that's been around in the field for about 20 years that we're now starting to chip out towards a solution thanks to the sensitivity and the new wavelength range offered to us by JWST. And this is a project that we've been doing as part of the Massive Stars group here at Space Telescope. So everyone's kind of listed there, and a bunch of other collaborators that have been included. And special mention to David Law, who has been like a really integral part of this project. So I kind of wanted to say this is probably a little bit like outside of people's areas of thinking, I'd imagine, for most of the audience. So I want to talk a little bit about what I mean by massive stars and what's going on in the field. So I'm talking about massive stars in the context, I would say anything that undergoes core collapse, basically you would call a massive star. And so you can kind of see some of the different topics this ties in with I've listed here. If you're interested in feedback, these things are making a ton of output for the surrounding medium. They are evolving into these kind of weird, rare evolutionary phases. So things like Wolf-Rayet stars, red supergiants, supernova, they were massive stars at some point. And similarly, they're also becoming black holes, neutron stars, gravitational wave events. And if you're looking early on in the universe, you're probably finding more massive stars. And this is, I suppose when I say the early universe, I really mean the low metallicity universe here, because if you're low metallicity, it's harder to cool. And so when you're collapsing into a star, you have a higher mass, basically, to begin with. And so if you're kind of interested in low metallicity physics of stars, mentioned already that there's a symposium that you might be interested in, and you should vote for that. I kind of also I'm interested in these stars from this feedback perspective, right? Because they have really strong stellar winds. So this is so I guess I'm showing you some of the key parameters here that you're interested in if you're characterizing stellar winds, basically mass loss rates and wind speeds to get the momentum and the NAG input, and also their ionizing flux. So these things are massive, but they're also very hot. We're talking sort of like on average maybe like 40,000 Kelvin. Maybe 1 million times the luminosity of the sun. And so you have this really, really strong UV peaked SED that's also overlapping with a bunch of metal ion transitions in the UV. And so you have all of this flux that's pushing on these ions, and you're ejecting a ton of material. And so you can kind of imagine that that might be something that's also metallicity dependent. I'll get into that later. So I wanted to show basically, well, I guess, for a little bit of context, there's a picture here of a massive stellar wind, but this is actually a Wolf-Rayet star, and you can kind of tell the star is just like this tiny little bit in the middle, and everything else is material that's been ejected a long time ago and has cooled down and only being illuminated in the infrared. What do these things actually look like? We have no idea, essentially. We kind of think that they're spherical balls of gas, And here's some simulations that have been coming out recently. So this is from the group that I was doing my PhD with in Belgium, in Leuven. And they've been working really hard on the first 3D hydrodynamical simulations of massive stars with radiative transfer. So you're seeing here what the stellar atmosphere might kind of look like in the UV and in the optical at specific line transitions. And this is kind of just to say that these are not like super nice, smooth, spherical things. There's a lot going on in the physics of the stellar surface and the winds. And they're also, this is a time-dependent process, right? So you're not just seeing a bumpy atmosphere, you're seeing a bunch of material outflowing with time, and it's kind of changing and shifting. And I kind of want to highlight this because if you take a snapshot of one of these simulations, right, you're seeing basically here a load of dense clumps and a load of material that's actually moving way, way faster than the outflowing clumps of material because they're less dense. And you're kind of seeing this velocity map here. The high density material is slow, where it's infalling, like this blue stuff, and all the fast material is lower density. And what happens then is that materials crashing into each other, and you have shocks basically within the wind. So most stars have like a fairly appreciable X-ray flux. And this is to mention that you can have processes going on in the wind that are much hotter and higher ionization than they're going on the stellar surface, right? So keep that in mind as we look at high ionization diagnostics. Obviously, like I say, we're not seeing these kinds of nice images, so we're studying these things with spectra. I'm showing here an example of an O star in the UV and in the optical, and you're seeing, I kind of just want to mention that there's, you know, these great big P Cygni line profiles, which are this absorption and emission profiles. Compared to the optical, you have just emission. I kind of want to talk about this a little bit in terms of the physics that we're probing from the two profiles. I guess people are kind of familiar already with like emission lines and absorption lines. You know, when you have this outflowing sphere of material, you have an emission profile. If you've never really thought too much about why we have this weird shape for a P Cygni profile, it's because in the UV, you have all these metal transitions that I mentioned before that are in between you and the star in the line of sight, and they're absorbing material really, really efficiently in that specific blue shifted region that's moving to you. So you have this blue shifted absorption component that can be as strong to completely saturate the line, so you're getting really no flux. And I want to mention this because this is telling you essentially exactly what the speed of the wind is, because all the material that's being blue shifted, that's being blocked, is basically material that's in the stellar wind. And you can read off the wind speed pretty well from that. So I want to describe a little bit about where we're at in the field of stellar winds before I go into some issues that we're talking about in this, and a little bit of self-promotion. So this is from UV and optical analysis with spectroscopic fitting of what we're getting from mass loss rates for massive stars across the luminosity range. And theoretical predictions are here in these dotted lines. There's the very established ones from the early 2000s are kind of like a little bit different to what we're finding from the data. And some of the newer predictions are lining up pretty well. So this is just sort of to say that we're doing a fairly decent job of being able to get estimates for these mass loss rates for anything like stellar evolution feedback from fitting now. And so we're able to do even better with Ulysses. So the stuff I was showing before was like a fairly small program from HST pre-Ulysses that I was working on. And now we have, you know, instead of 10 to 20 stars, we have 250 with 500 orbits across the LMC and the SMC. And again, something we're super interested in is this metallicity dependence of the wind parameters, because it's this, you know, metals and ion driving the wind. And here you can see with these, you know, 100 plus stars, trend between the galactic relation and the LMC and the SMC, you know, a solar, half solar, and a fifth, essentially metallicity. And so you're starting to get, with these statistical samples, actual relations between metallicity and wind parameters that you can apply to all kinds of things. And this is stuff we did basically with the Ulysses spectra, because you can do it straight from the UV. Doing full modeling in the UV and optical is a little bit harder, but we're working on it. Basically, this is just showing you a compilation of a couple of different papers in all these three regions. And so we're not quite there yet, but this is just to say that between the mass loss, the wind speeds, we'll be able to get full wind strength metallicity dependent relations thanks to Ulysses. And we're very excited about that, and that's coming up soon. So now that we kind of know what's going on with massive stars and stellar winds, I want to show you basically the problem I want to discuss in the talk. You have, again, one of these sort of plots of stellar wind strength. This is just, again, momentum, it's mass loss and wind speed combined, going with luminosity. And if you're familiar with spectral types, you're kind of seeing this nice, steady decrease of wind strength, and that's going along with the actual emission and absorption peaks of the UV profiles, right up until you get to this characteristic luminosity of about 5.2, and then everything just falls off a cliff. And we kind of have no idea what's going on here. Basically, anybody measuring mass loss rates for any of these stars has not been able to get a value that lies with the predictions from theory or with the general empirical trend without completely over-predicting all of the UV line profiles. So you can kind of see 07 and 09, I mean, this is almost photospheric. You're really not seeing any wind signatures in the UV. And it's a big problem. This is something that was sort of discovered about 20 years ago, and there's not really been much progress on getting a solution. There are a couple of different theories that have been predicted. You essentially have a situation where either there really is no mass loss and there's just nothing coming out of the stars anymore, or you're missing something and you're not seeing it in the typical diagnostics for some reason. So we keep that in mind. Let's zoom in on one of these stars. So this is an 09 dwarf star, 10 Lac. It's the same one that was showing on the slide before in carbon-4. There's almost nothing going on wind-wise. The highest mass loss rate estimate people could get from these from this spectrum was 10 to the minus 9. It's about an order of magnitude below what you would predict, or if you were following a general trend. So this is kind of, it's a long-standing problem, but it's also kind of beneficial to other fields. So for example, if you wanted to look at a really bright source nearby for another purpose that doesn't have any kind of stellar wind, it's a nice simple O star, then you might use it, for example, to flux calibrate a new telescope like JWST. And so they took Miri observations with the MRS of 10 Lac, and this is work that David was leading. And around about the same time this is going on, we're sort of establishing the Massive Stars group at Space Telescope early last year. And then at some point, David pops into the Slack channel and says, does anybody know anything about broad emission lines in Neon 5 for stars like 10 Lac? I have no idea what's going on. They're messing up my calibration. And so this cues a ton of discussion that's basically been going on for the last year of us trying to figure out what's going on for these stars. And this is what the spectrum looks like in the infrared. You have pretty significant emission lines when you're not seeing anything in the UV or the optical. These are broad, 1,000 kilometers per second at least. That this is telling you it's coming from a wind, it's coming from an outflow. There's really no other way to get this kind of stuff around these stars. And so this is really exciting for us. We finally have a method to go towards trying to get diagnostics of outflows for these stars. And I was mentioning before, the different line profile shapes we have in the UV and the optical. They're probing different processes, the resonance and the absorption and the recombination in the optical. This is another brand new diagnostic, basically. So I talked a little bit about line formation. How do you end up this weird flat-topped profile? Is that you have essentially an optically thin shell of material and you're losing absorption from the central region, right? And these aren't completely alien line profiles. You see stuff like this for Wolf-Rayet stars. You see it, this animation is actually from a supernova talk that I borrowed. And you can then say that we're probing a completely different physical regime, right, than the way the lines are forming in the UV and the optical. You're seeing something that might be consistent with the lines can only form beyond a certain radius because the conditions aren't met closer in. And so we have this nice semi-empirical relation to try and see if we can get any idea of what's going on for the wind parameters from these lines. And you don't really have to look too much at this, but it's just to say that the line strength is primarily set in this case for these lines because we have this nice optically thin shell scenario by the mass loss rate, how much material is there, and also the abundance, essentially, of the ion that you're measuring. And so here we have a plot using this relation of the ionization state against mass loss. And here you're assuming, say that all of the emission of neon is in neon 5 and 6, because we don't see any neon 4 or 3. You could do the same thing for the oxygen line that we saw in the further infrared. And these are the theoretical predictions I was showing earlier. And this is really a pretty strong lower limit on how much material has to be in the wind for you to be forming these line profiles. It's kind of tough to push below this without, reducing the line strength. And so we have now, for the first time, lower limits as opposed to upper limits from the UV and optical on the mass loss rates. And so what does it look like when we plot the two diagnostics together? Again, this general trend from a sample in the Milky Way, theoretical predictions, and you're increasing the mass loss rate by an order of magnitude in the infrared than you are in the UV and the optical, which is very exciting. This looks like essentially you've solved the problem, right, for this star anyway. And I kind of want to talk about then our two different scenarios of, was there any material in the wind, or are you missing it? How do you end up missing all this material in the UV and the optical? One of the suggestions is that essentially you've ionized out all the typical diagnostics. So this is a wind simulation of an O supergiant on the left and an O dwarf like 10 lac on the right. And if you have a supergiant, the wind is very dense, and so it can cool super efficiently. As I mentioned, you have shock heating from all the material crashing into each other, and you're getting to way, way higher temperatures than you are just from the photosphere. And so if you have a really low density wind, like an O dwarf, you can shock heat all the material, and then it can't cool back down. So you could have a scenario where you have essentially just a really hot wind that you're not seeing in typical diagnostics, but you might see it in things like the infrared. You might see it in high ionization lines like neon 5 and 6 in the infrared. And these are simulations and ideas that have been sort of brought up in the past 10 years. The key papers there. Everything's solved and we're all happy. Not quite. So there was another calibration source. This is Mu Col, another late O dwarf, almost the same star as 10 lac, and you don't see the neon 5 emission line. So you're kind of throwing a spanner in the works a little bit, and we're wondering, is this really a general solution to this issue, or is it just something weird going on with 10 lac? And so you have to start, asking around, has anybody else observed O stars with JWST in the mid-infrared? They're not only good calibration sources, they're also great for if you want to do dust extinction mapping. And so a couple of the dust surveys that have been going on from Marjorie and Sasha, some of which is led at Space Telescope. We now have 8 essentially detections of this line. Some of them are a bit cleaner than others. And I kind of want to highlight here that this is 10 lac, and the signal to noise is great because it was the calibration source. It's by far the weakest line we've seen for any of these things. So anything else is much broader, much higher line flux. We're kind of interested in what stars this is forming in, right? So you have it in this dwarf, but we don't have a very uniform sample. These were kind of just picked out for lines of sight. And so you have things like a slightly earlier O star here, some binaries, et cetera, et cetera. So there's all kinds of stuff going on, and really what you want is to be able to go in and have a uniform sample across the luminosity range you're interested in. But for now, you have plotting the rest of these stars with strong detections on these wind parameter plots that I was showing before. And again, I would say falling in line with the trends. The wind speeds are a little bit more strange. And typically, when something's falling off a trend, I would say, oh, it's a binary, something weird's going on. The only 2 stars that lie on the trend are binaries. So we're really just scratching the surface of the physics that's going on in these systems. And we're really excited about being able to use JWST as diagnostics for O-star winds. This is a recently accepted Cycle 4 program where we're doing exactly what I was just saying. This is our proposed coverage, getting, filling this gap in the weak wind regime and trying to get see where we see the lines, what diagnostics can we, what constraints can we get for the massless diagnostics, and just showing you here a couple of the ones. These are from the whiskey and mead before, so data hopefully coming in soon. I think the first spectrum is like scheduled. It's like in flight ready or whatever you call it. The rest of them will be coming over the next year. And there'll be a few more also with the program from Marjorie. So that's kind of all I wanted to say. We have a brand new window into a completely different wind regime and line formation physics with JWST that nobody predicted for these O stars. You're constraining mass loss rates and wind speeds for any kind of purpose you might be interested in, using the infrared for these stars for the first time. And this is really just like the start. We're very excited to be able to do this for a proper sample of these things. So thanks for listening. I hope this was interesting. Happy to take questions.
All right, questions for Calum.
I was just curious for the neon 5 line width.
Yeah.
Matches at all the absorption trough information in terms of just loss.
Yeah, so actually the best estimate you can get for wind speed, for example, for 10 lac from the UV width matches pretty well with the width of the neon 5 line, which is interesting. But again, this is 10 lac. For the other stars, the UV is a little bit harder. So for example, the ones that were in the dust extinction survey, they don't have the nicest UV spectra because they're, extinction of 5 at least in the visual band. And so this is something that we're really keen to try and figure out for the rest of the sample. For the other one, this star here with the nearly 3,000 width, that one also matches fairly well. I mean, within a couple hundred kilometers per second. There's an O5 star and an O9 star in this system. So you have a UV spectrum from the O5 star that's giving you a really nice UV P Cygni profile, basically. So you're pretty confident for that one. But again, it kind of is the question of like, this is coming from the normal O5 star. You're getting it across the whole spectral range. What's this telling you across different O star conditions, basically? Yeah.
Additional questions?
Should probably know this, but does 10 lac have like a nebula around it that's been observed? And does it kind of have weird emission line features that you wouldn't typically see in like a less massive O star?
It's a good question. I wouldn't have thought so, considering they use it as like this nice spectral standard and there's nothing weird going on nebula-wise. You also agree there's no nebula? Yeah. So nothing for 10 lac, but for other stars, something to look into.
So thinking about Neucall versus 10 lac, is there any is there any hint that variability could be the reason there? Is there any in the theory or even the observations in the UV lines where we might expect these lines in the infrared variable? In other words, should we be going back and looking at the stars again?
Yeah, I mean, this is the question we had. So for 10 lac at least, right, there were 2 epochs, I guess, and the line was pretty stable across like maybe 6 months or something. I think the baseline for that was. I wouldn't be surprised if something variable was going on. I would be surprised if it was variable enough for the line to completely disappear and come back. But again, this is kind of new territory. If this is being formed from like a typical steady state wind scenario, then sure. But if something else is doing it, like a real phase dependent phenomenon, like there's a companion or a pulsation or something like this, then why not? So yeah, I do think it would be nice to do monitoring of these things.
And is this right? This is the only one we have so far that isn't a weak wind, that we don't see the wind.
So far, this is the only one that's in the weak wind regime that has a nice enough spectrum that you could say whether or not there's a line there or we don't see the line. So I'm very happy that you observed them with the dust map survey, because otherwise these would be the only two and you would have no idea. Yeah.
I see this is neon 5 at 14 microns. I'm wondering if you see any neon 5 at 24. Yeah, 24.
Yeah, you got this one at 24 as well. You have.
Give you anything interesting?
So the only thing I've done with the ratio so far was to see if it was like realistic with what you would assume for, you know, like case B recombination, and so it seemed fine. I think what will be really interesting is doing actual atmosphere modeling of these things. So one of our collaborators, John Hillier, who works on the CMF-Gen code, if you're familiar, he's been running the first models of spectral predictions of these lines in the mid-infrared, putting in the atomic data and extending the atmosphere of the model, et cetera, et cetera. The ratios are a little bit less straightforward in that scenario. You know, you can have other transitions in the UV that are influencing, like pumping the transitions in the infrared. You could have different situations for different lines. Maybe your abundances and this kind of thing are interesting. Maybe they're forming in different areas. I mean, these are both from the same state and they're not that far away, so I'd hope that it's pretty consistent, but I think remains to be seen, basically. Yeah.
All right, any last questions? All right, if not, let's thank Calum and also thanks so much for coming to HotSci.